So we have our algebraic equation. We also checked our algebraic equation by using the initial and final value theorem. So we know that the equation is good. And now our next step is to massage that equation into a way that we can apply the inverse Laplace transform to find our response in time. So the motivation is we have our equation in this form where we have the zeros on the top and the poles on the bottom of our equation. Remember, the zeros are the roots of your numerator and the poles are the roots of your denominator. And the technique that we are going to see, it's called the partial fraction expansion, which is going to rewrite our equation in this form. Now, we want in this form because this is very friendly for the inverse Laplace. So let's go over this partial fraction expansion, what it is, and how can we reduce the circuit into the one here on the bottom. Alright, so step number one is to find the roots of our equation. So if we have this equation over here, if we find the roots on the numerator and the denominator, then we're going to have the function in this fashion. But when we find the roots, we can have roots that are real and different. We can have roots that are complex numbers, or we can have roots that are real and equal, and we can have multiple of those. Sorry, here was real and different. Now, notice here that I'm just emphasizing the denominator because finding the zeros of our equation, so the roots of the numerator, they're actually not that important for this step here. Alright, so the algorithm that we're going to use is called the cover-up algorithm. So when the roots of your denominator are real and different, in order to find the respective residues, we're going to apply this formula over here. So we pick up the pole of interest and we multiply by our function, and we substitute the s by the pole of interest. If the roots of your denominator are complex numbers, you apply the same technique, the cover-up algorithm. The only difference is that you only need to find 1k for one of the complex poles. The other one is going to be the conjugate of that, which means that only the imaginary part has the opposite sign. But you do the same thing. You do the cover-up algorithm, which means that you multiply by the pole of interest with your s, and then you do the s, you substitute the s by that respective complex pole. Now, if the roots of your denominator are real and equal, and you have multiple of them, this is where things can get a little bit more complex. In literature, there are two different ways of achieving the result, but it's outside of the scope for this video for now. I'll do a video later on explaining how to do these roots of the denominator when they are real and equal. Alright, so let's go back to our example. And one of the things that I'm going to do is I'm going to have my function written in different formats, and we're going to use the format that it's better for our cover-up algorithm. So this is the original one. Then you have here with the common denominator, and the goal is to go from here to this one where we have these residues and the poles on the bottom. Alright, cool. So we already know the roots of our denominator. We calculated these before, which are the poles. We have one at s equal to 0, and we have a complex number here with -1 plus or minus 2i. Alright, so if I rewrite my original equation over here, I get a third format, which is this one over here, where I have, instead of having in this form, I have the poles represented on the denominator. Now my goal is to expand that to this format where I have the poles isolated from each other with the respective residues or k's. Alright, so now let's focus and find this k's. So let's find k1, applying the cover-up algorithm. And in this case, for our k1, because k1 is a real root, I'm actually going to use my IL of s in this format. That's just because it makes my life easier. Alright, so k1, which is that value over there, it's equal to the pole of interest, which is my s, times IL of S when S is equal to 0. That's my pole at S equal to 0. So if I put that S over there, cancels out, and if I substitute S by 0, you see that you get only 10 divided by 5, which is equal to 2. So K1 equal to 2. For your K2, the complex ones, you do exactly the same thing. So I have here now the expression that I'm going to use is this one, because now I have my SR complex number, so it's easier to put it in this format. And I have a complex root, so I'm going to substitute here I'm going to multiply my IL of S by that function, and my S is going to be equal to -1 plus 2i. Alright, so if I plug these over here, so notice that this term cancels with this term, and then wherever you see S's, I literally substitute by -1 plus i. And you're going to get 1 over 4i in Cartesian format, and in polar form you get a magnitude of 0.25 and an angle of -90. You can do these complex number additions, multiplications and divisions and subtractions by hand, but I'm giving you here a complex number calculator, and if you put the expression with just the Cartesian format, it gives you the answer in Cartesian and angular format. It's pretty cool and easy to use. Alright, so that's my K2, and my K2, the conjugate of that, which is that symbol over there, that means that only the imaginary part of your complex number flips the sign, which means in polar form it's just swapping the sign of your angle. And you get your K2 prime, or K2 and the conjugate equal to that. Alright, so plugging things where they belong, we had the K1, K2, and the conjugate of K2. I'm literally just plugging those values here, and I get 2, the 0.25 with -90, and the 0.25 with 90. And this is my equation ready to be used for the next and final stage.